Hello everyone, welcome to Engineering Explained channel. In this session, I am going to discuss the derivation of Bernoulli's equation from Euler's equation. If you have not subscribed, kindly subscribe my channel. If you are subscribed, kindly comment and share. Here, the Bernoulli's equation that can be derived from the Euler's equation and how that is derived, I am going to discuss here. The first I am going to take the Euler's equation of motion derivation. What is the Euler's equation of motion will take, and further we'll take the derivation of that. This is equation of motion in which the forces due to gravity and pressure are taken into consideration. This is derived by considering the motion of fluid element along a streamline S. Here the one fluid element is considered that is moving along the streamline is taken into consideration. But taking it, we are going to derive the equation. Consider a streamline in which flow is taking place in S direction as shown in figure 6.1. Here we are going to consider the streamline flow which is taking place in the direction of S. Then consider a cylindrical element of cross section dA and length ds. In this flow line, we are going to consider the one element whose cross section is a dA. That is, element is a cylindrical element whose cross-sectional area is dA and length ds. Then the forces acting on cylindrical element are on this cylindrical element. What are the forces are acting? The first one, pressure force PdA in the direction of flow. The pressure force, the force due to pressure, that is the pressure multiplied with the cross-sectional area. That pressure force which will be acting in the direction of S. That is the first force. Second one, pressure force P plus dou P by dou S into ds into dA opposite to the direction of flow. Here the pressure will be changing from for this length of ds, and that change in the pressure is taken into consideration, and therefore the total pressure will be P plus dou P by dou S. That is a pressure force which is acting in at this point at the distance ds. And if you multiply the cross sectional area and that force which is acting, the pressure force in the direction opposite to the this direction of flow. Third one, weight of the element rho g dA ds. The fluid element is having the weight, and that weight can be taken as the its mass multiplied with the acceleration due to gravity, and here the rho multiplied with the volume, this one, and density, that will give the mass multiplied with this g will give the weight of the fluid element in the direction downward direction. And let theta is the angle between the direction of flow and the line of action of the weight element. This is the theta. That angle is the angle between the that direction of flow and the line of action of weight in the downward direction. Then the resultant force on the fluid element in the direction of S must be equal to the mass of the fluid element and acceleration in the direction of S. The resultant force, what is there? Out of this, all the three forces, what the resultant force is acting, that must be equal to the mass of the fluid element multiplied with the acceleration in the direction of this S direction. What is the acceleration is acting? That is the AS. And by considering this one, we can write the equation. That is the pressure force in the direction of S, the PdA, the pressure force in the direction opposite to the S direction, that is taken as the P plus dou P by dou S ds into dA, which is negative because of the in the opposite direction which will be acting. And this is the weight component in the direction opposite to the direction of flow. Okay, in this direction, the weight component is taken. That is a rho g dA ds into cos theta. Okay, here this is the cos theta is taken. That is opposite by hypotenuse is a cos theta. Therefore, the here this rho g dA ds will be the force which will be acting in this direction. Okay, that component of the weight element in the direction opposite to the flow, and that is equal to, this is the mass of the element. The mass is the density multiplied with the volume. Now, density is the mass per volume and this volume, if you multiply, that will give the mass into acceleration in the direction of s is the as, where as is the acceleration in the direction of s. Now, as can be written as, the acceleration can be written as change in velocity with respect to time, where v is the function of s and t. It is a displacement and the time. The, that velocity is the function of the displacement and the time. And this acceleration can be written, taken as the with the partial derivation, that can be written as dou v by dou s and ds by dt plus of dou v by dou t. Okay, this partial differentiation of this, if you take, then we are going to take that as written as the dou v by dou s into ds by dt plus of dou v by dou t. And here already the ds by dt, what it is there, it can be written as v. Therefore, the v into dou v by dou s, the first term will be s ds by dt. If you take v, and v into dou v by dou s, and second one dou v by dou t will be remains. Okay, this dou v by dou t. If the flow is steady, this dou v by dou t is equal to 0. The change in velocity with respect to time is 0 for the steady flow. Then as, the acceleration in the direction of s, can be written as this first term only, that is a as equal to v into dou v by dou s. And substituting this as value in equation 6.2. Okay, that substituting the value of as in 6.2 and simplifying the equation, we will get, that is simplifying that equation means here the PdA will take, and minus of PdA will be get cancels, and this second term minus dou p by dou s into ds dA, that only remains. This is a term. Okay, the simplification, this term, the PdA will be get cancels, and the remaining term we are going to write here. And the second, again the rho g dA ds into cos theta will be remains, and rho dA ds will be mass, and acceleration will be v dou v by dou s. Now dividing by this term, dividing by this equation by rho ds dA, and here ds dA will be get cancels from the first term, rho will be in the denominator, dou p by rho ds will be remains, and here the rho second term rho dA ds will be get cancels, and the g cos theta will be remains, and that can be written as here again the rho dv ds will be get cancels, v dou v by dou s will be on the right hand side, and this can be written as dou p by rho ds and plus g cos theta, that is plus v into dou v by dou s equal to 0. Okay, further that equation is written here, the same equation, the rho p by rho dou s plus of g cos theta plus v into dou v by dou s equal to 0. But from figure 1b, okay, here the 1b what it is taken, there is a 1b, this equation. Here you can write the cos theta is equal to, cos theta is equal to opposite adjacent by hypotenuse. The cos theta is adjacent by hypotenuse. That is a dz by ds. Then the cos theta dz by ds, and here the cos theta dz by ds we can substitute in this equation. This equation can be written as 1 by rho into dp by ds plus of g into dz by ds plus v dv by ds equal to 0, or we can write dp by rho plus of g dz plus v dv equal to 0. Here ds we can, from the common we can take and send this side, right hand side, that will become say 0. Okay, that becomes a 0. And this equation again rewriting dp by rho plus d dz plus v dv equal to 0. The equation 6.3, this equation is a 6.3. This equation 6.3 is known as Euler's equation of motion. This equation is the Euler's equation of motion. Now further moving for the deriving the Bernoulli's equation from the Euler's equation of motion. How you can get the Bernoulli's equation? Bernoulli's equation is obtained by integrating Euler's equation of motion 6.3 as, okay, the Euler's equation of motion that will be integrated. After integration, we are going to get the Bernoulli's equation. The integration of dp by rho plus of integration of g dz plus of integration of v dv is equal to constant integration, constant 0, integration of the 0 will becomes a constant. If the flow is incompressible, rho is a constant, and then the does not this integration of the rho will not be there because it is a constant. Then dp integration will be p by rho, and g will be constant, and gz will be becomes a z, gz plus of this v into dv integration will be v square by 2, that is equal to constant. And the same equation is written here, p by rho g, the equation g is divided with g throughout that one, we are going to get p by rho g plus of z plus of v square by 2g. And rearranging this equation, there's a p by rho g first term, the second one v square by 2g plus of z is equal to constant. And this equation, what it is there, this is a Bernoulli's equation. The Bernoulli's equation, p by rho g plus of v square by 2g plus of z is equal to constant, is the Bernoulli's equation, where these terms are p by rho g equal to pressure energy per unit weight of the fluid or pressure head, and v square by 2g equal to kinetic energy per unit weight of the fluid or kinetic head, and z is a potential energy per unit weight of the fluid or potential head. At any section, if you take the all the energies, that is pressure energy per unit weight or plus kinetic energy per unit weight plus potential energy per unit weight of the fluid will be remains constant at any cross section if you are going to take. That is the Bernoulli's equation. That is the Bernoulli equation, or we can say pressure head plus kinetic head plus potential head equal to constant at any cross section we are going to take. And that's why that is applied for the different applications. And I have discussed in the other session the applications of the Bernoulli's equation. Assumptions made for this deriving the Bernoulli's equation. The following assumptions are more in the derivation of Bernoulli's equation. First one is the fluid is ideal, that is the viscosity is 0. The viscosity is the resistance offered by the one layer of the fluid to the another adjacent layer of the fluid. That resistance what we will call as a viscosity. And in the ideal fluid there is no resistance. There is no resistance for the one layer to the another layer. That is the ideal fluid. That is ideal we are going to consider. No real fluid having the zero viscosity. Second one is the flow is steady. The rate of flow does not changes with respect to time. That is the steady flow. The flow is incompressible. Density of the fluid does not changes during its flow. That means the fluid does not compress during its flow. That is called as incompressible flow. Next is the flow is irrotational. The fluid particles does not rotate about their own axis while flowing. That is called as a irrotational flow. These are the assumptions which are made for the deriving the Bernoulli's equation. This is about the derivation of the Bernoulli's equation from the Euler's equation. The derivation of the Bernoulli's equation from the energy equation, by considering the energy equation, I have derived in the another session, and applications of the Bernoulli's equations also I have taken in one session, and links for those I will provide in the description. Kindly you can refer and watch those also. Thanks for watching. If you like, share, subscribe and comment.